Any idea about the size of a virtual address? Actually, the size of a virtual address depends on the architecture and OS used. And in most modern OS, the size is determined by the number of bits that are used to represent it. And the common sizes are 32 bits and 64 bits. So this is the illustration that we've had in the previous topic, which is of the simple na paging. So we have one page table that maps the logical address and the physical na address. So we represent the logical address with the page and the offset, and the physical na address with the frame and the offset. And these are just the simplified addresses to keep the explanation simple. So in reality, we have a 32-bit address for the logical addresses, wherein the first 20 bits represent the virtual page number, and the next 12 bits represent the offset. So with 32-bit virtual address, the address space is limited to 4 gig, meaning the system can address up to 4 gig of memory. So anyway, assume that we have a 32-bit space and a 4 kilobytes page size. So assuming that we have a process size of 2 raised to 32 bytes, and each page size is 4 kilobytes. So that it equivalent to 4,096 bytes, which is equal to 2 raised to 12. Now, the total number of pages in the page table would be 2 raised to 32 divided by 2 raised to 12. So we basically just divide the process size by the size of the page. And that would give us 1 million. So that means that we have a total number of 1 million pages in the page table. And since each entry is 4 bytes, so that would be 4 bytes times 1 million, that would be 4 megabytes. And it means that this 4 megabytes is needed just to store the page table. It is not bad, except that each process needs its own page table. So if we have 100 programs running, so that means that we are going to need 400 megabytes of page tables. So this is how it's illustrated. We have a large program, assuming that it is 2 raised to 32 bytes. Now we are going to divide it into pages, and the page size would be 4 kilobytes assumption. So to compute for the total number of pages, we simply have to divide 2 raised to 32 by 4 kilobytes, or equivalent to 2 raised to 12. Okay, which means this will give us 1 million entry in the page table. So that would give us 1 million entry. So each of this entry would be 4 bytes. Okay, 4 bytes. And since we have 1 million entry, again, this would be costing us 4 megabytes just for this one big page table. And note that the page table also resides in the main memory. So if it's too large, it may not be able to fit. Okay. So one solution would be to use multi-level na paging or hierarchical page tables, wherein we break up the logical address space into multiple page tables. And as you can see here, from a very large table that contains 1 million entries, we now have broken it up into smaller page tables containing only 1,024 entries. Okay, and each of these page tables then will be of size 4 kilobytes then, since 1,024 na lang yung entries. And of course, the page table's role will be the same. It is to map the pages with the physical or the logical address with the physical address. So for example, this page 1 is mapped with this frame, which is of the address FF. Okay, so we can access this data in this specific frame. Now, the idea of multi-paging is that we break the tables into, we break the big page table into smaller page tables, where in these page tables will be residing in the main memory. So those page tables only that are required by our execution will be residing in the main memory. So those that we don't need will be in the secondary memory. Since these are in the main memory, of course, they will have addresses. So how can we access these page tables? Okay, so what we need is to have one outer table that will be like a tracker or a pager of our page tables. So this outer table will also be 1024 entries, which means that it will also cost us 4 kilobytes. Okay, so what the outer table contains is the addresses of the page tables in the main memory. So it contains the physical address of our page table. So for example, this page table 1 or PT1 is in the address 92 in the main memory. This PT2 is in the um, FA in the main memory. And then this PT3 is on the disk on the other hand, since it's in the secondary in the memory. Okay. And now the question is, how are we going to access all these information or addresses? Or how do we translate the logical address into the physical address? So what we do is, instead of having a 20-bit na virtual page number, we will be breaking it down into two na 10 bits, where in the first na 10 bits will be referring um, to the address of the page table. So address of the page table, and the inner would be containing the physical na address of the instructions that we need. Okay, and the offset will be the same. So let's have an example. But take note, this outer na page table, the main na table will always reside in the main memory, since this will be we are going to use this main table to always access our smaller na mga tables. Without this, we wouldn't know where the smaller tables are residing. Okay, now this outer table contains all of the addresses of our page tables. Now let us try to have an example. Now we have this 20-bit na virtual page number wherein the first 10 bits contain FA. So what does it mean? So that means that we are going to look here in our page table, may outer na page table. And as you can see, it is same FA. So that means that we are referring to this page table 2. So we take out page table 2. Oops. Sorry. So we take out page table 2. Now we look at the next na 10 bits. So it points to FF. So FF refers to the physical na address of the actual data that we need. Okay, so we are now able to access the information that we need so much using these addresses. The first na 10 bits, which refers to the address of the page table, base address of the first table, and the next bit that refers to the physical na address of the actual instruction that we need. And of course, the offset will be used to look through the contents of this frame, specific na frame. Okay? Now, only the outermost na main table will reside in the main memory, and the other na page tables will be brought to main memory as per the requirement, because at a particular time, we do not need a complete na page table. So if we go back here, if we don't need page table 2 anymore, so we take it out of the main memory and we put it in the secondary memory. But we still have access to page table 2 since it is indexed here. Okay, so we know where it is. And also we can save much na memory space because the outermost page table can fit in exactly one frame. So as you can see, we have the outer table which only size, which is only sized 4 KB, so it can fit in our main memory. Okay, compared to super one large na page table which will cost us 4 MB. Okay, now how does it actually exactly save space? So just using one page na table, which contains 1 million entries and four bytes each na entry, that would cost us 4 MB, right? So without multi-paging, we need the whole table to access the data that you need. And each of the entry is 4 bytes times 1 million, that would be 4 megabytes. But when we are using multi-paging, here we see that this points to page table 2. Okay, so immediately we eliminate other page tables and focus our search space on page table 2. And with that, since the outer table is 4 kilobytes and page table 2 is only 4 kilobytes, so we only need a total of 8 KB only to access the data that we need. So that really made it super efficient. Okay, now that's all, and see you in the next video.